We're going to talk today about geometric sequences. So you learned last week, Friday, arithmetic sequences, and those work for when we're adding numbers or subtracting numbers. And this time we're going to talk about geometric sequences. So we're looking at things that are exponential, that grow by multiplying, whether we're multiplying by a whole number or by a fraction. And so we're looking for a common ratio. So let's go ahead and jump in with our first one. So we're looking for a pattern that is happening between 2 to 6, 6 to 18, 18 to 54, and you can see pretty quickly you're multiplying something. 2 times what gets you 6? Does that same number times 6 get you 18? So you're actually multiplying by 3 each time. So this by 3, or little times 3, is your common ratio. So your common ratio here is 3, and we can do a CR. They use actually the letter R for a common ratio. So we'll start with our recursive. That is just finding the next value. You don't really need a formula for this like we talked about in arithmetic, but sometimes you have to make a general formula for recursive. So here's our formula for geometric for recursive. We have a sub n, which we know is we're looking for the next term. And then a sub n minus 1 is the now term. And so we're like, what do we know now? It's the last one that we know. And then we have times r, the common ratio. So for this one, if we're looking for the next term, we keep it as a sub n, because it's just the next one. And what we know now, the last one that we know, is 54. And then we're multiplying times our common ratio of 3. Use a calculator if you need to. This, when you multiply it out, gives you 162. So your next value is 162. All right, so recursive is pretty simple, but however, we're going to go into explicit for geometric, and this is where you're going to use the most. So it looks a little different from the explicit for arithmetic. So we know we're looking for any term in the sequence. We still have to know the common ratio. We're using the same pattern as we did in the first one. But this is your formula. You have a sub n, so it's any term you're looking for. A sub 1, your original first value in your pattern. And then you have times r raised to the n minus 1. So the n at the top is actually your term variable that you're looking for. So what value you're looking for. So we're going to try to find the 7th term in this sequence. So we already know that our r is 3, because we know we multiply times 3 to get to the next level. And now we're going to plug into our formula. So we're looking for the 7th term, so we're going to write it as ace of 7, because that's what we're looking for, is equal to, we're looking at our very first term, and our very first term in the sequence is 2. So we're going to put 2 times, our common ratio is 3. And now what we're looking for is the n, and that was replaced here, so we're putting 7 minus 1. So now let's simplify that down. That's the ace of 7th, we're looking for the 7th term, 2 times 3 to the 6th. Now remember, you're going to do 3 to the 6th first. You can use your calculator for that. So 3 to the 6th power, let me see what it calculates as. 729, and then times 2. And so you would get the 7th term in this sequence is 1458. And that would be your answer. Now, this is another example. So I want you to try to find the common ratio and find the recursive, work it out, and the 13th term with the explicit. Pause your video, try it, and then come back and check. All right, so we found that our common ratio was 4, so times 4. And to find the next term, we plug in 64 times 4, and we got 256. That's our recursive for the next term. For the explicit, for the 13th one, and I think I had a plus written here a while ago, sorry about that, for the n minus 1, it should be n minus 1, not n plus 1, I think I had it plus. So we're looking for the 13th. So when we put all of our values in, we get a very large number. We definitely wouldn't want to work that one out on paper. So we want to have a good formula for that. So we're going to move on to writing an explicit formula for this pattern. So here's our same pattern. we're going to create a formula. So that means if I ask you to find the 13th, and then I ask you right after to find the 100th, and then I ask you to find the 3rd, you would not have to redo all the work each time. You're coming up with a general formula. So we're going to start with our explicit formula, our general formula, and we're going to plug in what we need. We already know that our R is 4, and we already know that our first term is 1. So we're not going to put anything here because this is a general formula. So we're going to keep it a sub n. We're going to put 1, and this is important. You have to put that first one, even if it's 1. And then times, our R is 4, and then we're going to leave it as n minus 1. So this would be our general formula, explicit general formula for this pattern. For this pattern only, but is an explicit formula. So now I could ask you to find the 10th, and all you have to do is plug the 10 into where the n is and calculate. This is not the same thing as this. Do not simplify it down to that. That is not correct. All right, so we're going to look at these two different ones, and I'm going to say that for these two formulas, these are two formulas written, let's see if they're equal. Are they the same? This is a common mistake that a lot of people make. So let's say I ask you to find the 13th term. So oftentimes what people think, if we're putting in 13, we would have ace to the 13, and we'd have 2 times 4, 13 minus 1. So we'd have ace to the 13th equals 2 times 4 to the 12th. Do not make a mistake and multiply these first. Remember, exponents get done first. So we raise 4 to the 12th, which is 167772216, and then multiply it by 2. So our final answer, 33554. Let's make that a little more readable. 3355443. Add your commas if you'd like. And then our answer is easily there instead of multiplying. Okay? If we look at this one the same way and we put in 12 and we say, okay, this is 13. Ace of the 13th, 8, and 13 minus 1. Ace to the 13th equals 8 to the 12th. And we put this one in our calculator, 8th to the 12th power. It'll give us an E, and that E is, remember, scientific notation. So you'd have 6.8719476674, and then it has an E to the 10th. That means we would actually move our decimal places 10 places over positively, and that's our number. So notice these are very different. They look the same, but don't make the mistake here. So we're going to look at another way where we can see, can we determine what a number is, or what the n would be, what the value would be. So our procedure, we have to make sure we find the common ratio first. That tells if it's geometric. Then we use the formula to calculate. Now for these, I want you to determine whether they're arithmetic or geometric or neither. So I want you to look, are you getting a common difference or common ratio? And that will tell you whether they're arithmetic, or if you get neither, then they're neither one. They're a pattern maybe, we just may not be able to easily find it. So pause, see if you can identify it, and then check your work. All right, so on A, you should have found that it's arithmetic. There was a common difference of 6, adding 6 each time, get us to the next level. On B, we started out, looked like there was going to be a common difference, plus 2, plus 2, plus 2, then all of a sudden it went to plus 6. So here's a great reminder for you. Do not just assume and do the first 2 and think that's it. Look at the whole pattern they give you. So this is actually neither. This is not an arithmetic or a geometric pattern. C, if we multiply by a half, 1 times a half is a half times a half is a fourth times a half is 1/8. We get geometric because we have a common ratio of a half. You can have negative common ratios just like you do with negative common differences. All right, so we're going to look at a couple well-known patterns, and then we're going to do kind of a tougher problem where we give you something different. So the next two, this B and C that we're going to do, are some famous patterns that were created, and you're actually going to do a little activity with them. So this is a pattern. It starts with 1 at the top. The next level is 1, 1, then 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and I want you to see if you can guess what the next two levels are. Pause the video, try it, and then we'll see if you're right, and we'll talk about what it is. All right, here's the next two levels. This is actually a pattern, very famous pattern, called Pascal's triangle. And you're going to do a little bit of research on this to understand a little bit more about this and how it came to be on a separate document. So you'll see that you'll learn a little bit more about why this works, what this is about, how he discovered it. So if we look kind of with the pattern, if you didn't get the pattern, if you'll kind of notice, this is a big triangle. You can think about it here. And you'll notice the ones are on the outside. They run down the side here and here. And then you also can see that 1 and here is 1, 1, 1. So we look in between 1 and 2. We added these two together, and that got us 2, and then the 1's on the outside. And then 2 and 1 is 3, and 2 and 1 is 3, and the 1's on the outside. 3 and 1 is 4, 3 and 3 is 6, 3 and 1 is 4. And if you look down here, these follow a pattern too. 1, 2, 3, 4, 5, 6. And this one's 1, 3, 6, 10, 15. There's a pattern. And 1, 4, 10, 20, 1, 5, 15, 1, 6. So if you went on and did the next level, you think about 1 and 6 equals, change the color here, 7. Our 1 goes out. 6 and 15 is 21. 15 and 20 is 35. 20 and 15, again, is 35. 15 and 6, we have 21. See how this repeats. And 6 and 1, we have 7, and then 1 on the end. So this will continue forever, so you'll learn a little bit more about this. So let's go to our next pattern. So I want you to see if you can find the next 3 terms. So I want you to look at the pattern, see what you think is happening. So we have 1, 1, 2, 3, 5. So take a minute and see if you can figure out what the next 3 terms are. All right, so our next 3 terms are 8, 13, and 21. So if you got that, you know how the pattern works. If you didn't, let's look a little closer. We start with 1. 1 plus 1 gets us 2. 2 plus 1 got us 3. 3 plus 2 gets us 5. 5 plus 3 gets us 8. 8 plus 5 gets us 13. 13 plus 8 gets us 21. And it continues on forever. This is called Fibonacci's Sequence. And this is the second one you're going to do a little research on. These are very famous. They're used for certain purposes. And you're going to try to figure out how they're used in today's time. So now we're going to do a little harder problem where I give you information that you haven't kind of seen before. So I'm going to give you All right, so I'm not sure what happened to my recording there. So this is our Fibonacci sequence, and we're going to learn a little bit more about this one. So here's your next 3 terms. All right, so this is going to be our challenge problem. And this is pretty tough. So I'm going to give you a to the 5th, and I'm going to tell you that this is a negative 16/27. So I'm using a fraction, and then I'm going to give you the R, which we know is our common ratio, and our R is 2/3. And you are going to figure out what some values, what this would be for the what the explicit formula would be, and also what the first 5 terms of this formula would be, the sequence, geometric sequence. So we're going to start with just our formula. So go ahead and write down your explicit formula for geometric, and then we're going to plug in and start looking to see what we have. So we've got to look at what we're giving. They're telling us that ace of 5 equals negative 16/27. So they're saying that our fifth term equals this. So we know what our fifth term is, but we don't know what they use to get all that. So we're going to work ourselves backwards. We do know the R, and we actually know the N. The N is right here because they told us the fifth term, the ace of 5, or the fifth term is negative 16/27. So we actually know the N is 5. So we're going to take what we know and we're going to plug it in to our formula to try to find out what the very first term was, or the ace of 1. And that way we can start building our formula and also building our pattern. So let's go ahead and plug in. So we have ace of 5. And we know that ace of 1 was here. That's what we're looking for. Our ace of 5 we're going to replace with what our value is. So negative 16/27. And our ace of 1 we don't know, so it's going to stay as ace of 1. We do know our R. Our R is 2/3. And our N minus 1 we know was 5 minus 1. And so now we're going to simplify down and we're going to solve for the ace of 1. So try it yourself, then come back and check. So once we plug everything in and we use our calculator, 2/3 raised to the 4th, we get 16/81. And then we're going to clear the fraction, or we're going to get the ace of 1 by itself. So I just multiplied the whole thing by the reciprocal, 81/16. So, of course, that cancels out this side here. We're left with ace of 1. And on the other side, when we multiply, the 16s cancel out, and we're left with 81 divided by 27. It's a negative, so we get a negative 3. So ace of 1 is a negative 3. Now we know some information. So now we're going to go and find out start with our sequence. So now we know our first sequence, and now we know our R, and now we're going to go back and let's make an explicit formula. So we've got to make our formula. So go ahead and see if you can make a formula that will work for this pattern we're trying to find. Now that you know the first term, you know the common ratio, go ahead and make a pattern or an equation. All right, so now we've created the explicit formula for this pattern. We know our first term, and so our was given to do the explicit pattern, so this would be the first thing we had to have. This would be our equation for the explicit sequence there, for our geometric sequence. And now we know the first term is negative 3, so let's now find the second one, third one, fourth one. So if we plug it in, we would do ace of 2 is our first term. We already know is 3. Our common ratio is 2/3. And then our second, 2 minus 1, would just be 1. So now we simplify that down. We end up ace of 2 is equal to negative 3, and 2/3 to the 1 is just 2/3. And we multiply that, and we end up these canceling out as 1 and 1, and we end up getting the second term as a negative 2. So our second term is a negative 2. All right, go ahead and pause and see if you can get the next 3 terms. So a total of 5 terms. We got 1 and 2. We want to get 3, 4, and 5. And there should be a little trick there. You already know a little bit about 5. All right, so we found our second, third, fourth, and we already knew our fifth, but I already worked it out just to prove that we're right. It works with our formula. And so that's how you would find an initial value if you were given what a total was and what a common ratio was. And you'll see some other variances of things where you have to do a little bit more in depth. But you just got to think about what the general formula is and move from there. So you've got some activities to work with geometric sequences, and reach out if you need some additional help.